All right. Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, January 27, 2023, the first Earth and Space Report of the new year. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a cool and moonlit, which is very apropos, moonlit winter's evening in my hometown of Rockport, Massachusetts. These Earth and Space reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our life-sustaining environment, and who wonder about the greater cosmos, including our place in space and moment in time. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on the 1623 Studios Community Access cable television channel. I'm grateful for the continuing interest and support shown by Rockport educators and students, Cape Ann cultural colleagues, cohorts of the Gloucester Area Astronomy Club, sundry Earth and space scientists and communicators, far-flung friends, family, and other curious folk. Thank you for participating. This evening, we are fortunate to have Dr. Caitlin Ahrens, whose talk is entitled Hot and Cold, Volcanoes and Hot Spots on the Moon. Dr. Ahrens is a postdoctoral research scientist at NASA's Goddard Space Flight Center in Greenbelt, Maryland. She received her BS in physics, astrophysics, and geology from West Virginia University in 2015, and a PhD in space and planetary science at the University of Arkansas in 2020. She has an outstanding record in public engagement and science communication through lectures, local radio, and international collaborations. Her main area of research involves remote sensing of icy surfaces and volatile interactions from the moon to the outer solar system at Pluto. My own connection with Caitlin is that we both serve as National Astronomy Education Coordinators representing the United States for the International Astronomical Union's Office of Astronomy for Education. Our 6-person team of volunteers spans a wide variety of educational and professional backgrounds in support of advancing astronomy education within the United States and beyond. So Caitlin, welcome to this gathering of fellow Earth and space explorers. The platform is all yours now.
Thank you so much, Bill, for that wonderful introduction. So hello, Earthlings. So I'm so excited to chat about the moon tonight. I'm usually all over the solar system and give a number of talks from Mars to Pluto and certainly the moon or certain topics that are covered throughout the solar system as well. So there's times when I even have to remind myself and go like, okay, where am I in the solar system that I'm going to talk about tonight? Okay, right. We're going to talk about the moon tonight. Fantastic. So let's go ahead and share the screen. So hot and cold. Here we go. So volcanoes and cold spots on the moon. So the interesting thing about the moon, though, is that we supposedly think that it's geologically dead. And in essence, compared to Earth, which is a very active planet, we have tectonic plates, we got very active volcano systems and earthquakes. We have landslides, we have erosional processes. We have all of this fantastic just climate and erosion and just all sorts of movement. Whereas on the moon, it's pretty much gray and cratered, and yeah, that's pretty much about it. But in reality, there's way more to it, though. There are different kinds of volcanoes. There are potentially different kinds of cold spots on the moon, and even just geology on the moon can be different kinds of fault systems and how those are formed, and lava tubes on the moon as well. And so all of this can really be explored, hopefully for eventual human interaction and exploration, but certainly through landers and rovers coming up in the future too. So let's, oops, well, well, now my computer decides, okay, there we go. So just purely just looking at the near side of the moon, which is on your left, and then the far side of the moon on the right here. So again, just purely just looking at this, though, it's like, okay, there's a couple shades of gray here and mostly craters. But if we were to really hone in on the different kinds of surfaces going on here, all the different bits of gray that you see here would actually be different kinds of minerals going on. Again, different kinds of geology. The really expansive dark areas here are mare. So mare meaning ocean in Latin. So most of this is very extensive volcanic goop, if you will, that has now been crystallized. So when the moon formed, you had all of this very slushy, dynamic, wonderful lava just slushing about. And so as it's being formed, and then the gravity of the moon, its pore insides are being pulled as it's now being tidally locked with Earth. And so now all of that is moving forward toward the near side of the moon. So this is why we have at least a good portion of this volcanic mare stuff on the near side of the moon. Now there are some bits, little itty bitty bits and pieces on the far side of the moon that are little lava basins and whatnot, but the very big extensive lava plains are very much on the near side of the moon. But because these are just very large basins that have just been filled up and filled up and filled up and then just crystallized, it's frozen in time. There's no vents per se to qualify it as volcanic in the sense of you need a mountain with a hole in the middle for stuff to spew out. Now, there are different kinds of volcanoes on the moon, which we would have as domes. And those kinds of domes would be very cute. So Gruithuisen region is a very fantastic, very textbook level volcanic domes on the moon here, though. So Gruithuisen is a little bit of a special case, though, because of the minerals that might be around Gruithuisen that suggest that these domes might be very young. Now, when I mean very young, we still don't really know the age of these domes very well, but we're going to be sending hopefully a rover or a lander there very soon. And when I mean soon, I mean within 5 to 7 years worth. So that's going to be very exciting to try to sample these domes. What are they made out of? We know that they're very fluffy, very light colored domes, probably a lot of aluminum, a lot of silicates going on there. So probably more quartz kind of minerals, aluminum, like I said, and nickel. But again, how are these formed? Why are they the size and shape that they are? Why are they found in that particular part of that mare region, and so on? So another interesting area that I'm going to take us to, though, is Lacus Somniorum. So that would be right around this area. Now, this has some interesting fun tectonics going on here, though. So I'm actually writing up a paper about this now. So hooray. But there's actually a lot going on here. Now, just looking at this image itself, though, it's like, oh, there's some really pretty craters. Maybe if you kind of squint and tilt your head, you can see some really cool like fault lines going on. Some beautiful extensive mare. But you may not be able to see what in the world is really going on just within this oval. So let's kind of deep dive into this, though. So we see this really beautiful, extensive, what would be a cliff turning into a graben to the northwest there. You see a bunch of, let's see, can I do a laser pointer? I can, haha. So you see this is a very beautiful cliff face, and then it branches out, which is really fascinating. You get all these like little bumps here and there. So we actually call these kapukas, which are very cute. It just means flooded islands, if you will. So this would have been material that would have been broken up mountains at one point and then just got flooded over and separated and just those poor mountains. But if we were to just look at a very simple map from the USGS on the different kinds of units going on here. So again, we're dealing with different kinds of geology, especially through that fault line, just kind of breaking right into that mare unit here. Imbrium So where all of those poor little mountains are being broken up here and there. So all of these different kinds of questions going on as far as the activity goes, the composition and everything. So what kind of geomorphology, meaning what structures are we dealing with within this area? How did that graben form? How did it just strike the surface? How did it break the surface and branch off like that? How and the why? Are there differences between the branches versus the main branch there? And then what's going on in the subsurface? So anything that happens on the surface, usually with any planet, there's or even moon, there's something going on underneath that's like, something would have pressurized underneath as well to make it crack or burst or kaboom or spew out stuff or anything. So what in the world is going on underneath that's making it do that? There's also pit craters around the area. So pit craters mean that there's some sort of collapsing of craters going on in the area. And then there's also domes, which I'll show you guys here in a bit. So there's little tiny volcanic domes that's one is near one of the branches and another one that is not near the branches. So what could that mean as far as like how these domes would have formed? Would they be roughly the same age? Would they have formed differently? Why would one be closer to the branching out graben area, not the other one? So these domes, so a very basic sense of just lunar volcanic domes in general, they're mostly in the Maria. But we need to account for all sorts going on here: viscosity, temperature, composition, the duration of your eruption, the rate of which you are erupting. And so think of it this way, though. I'm sure we've all done it. And if you just did it this morning, good on you. You get a straw and some chocolate milk and you blow into it and you make all the bubbles and everything, right? Let's be real. We've all done that in some point, or maybe just recently. And so if you think about it, though, there's so much factors going on, right? How thick is your chocolate milk? How big around is your straw? How quickly are you blowing into your straw to make bubbles? If you're blowing very slow, you're not going to get as much bubble action. If you are just kicking it up and really blowing into your straw, you're going to create some very big bubbles that it's going to splash all over the place. So there's a bunch of different factors in this too. So think of it that way with lunar domes. We're thinking about all the different kinds to get some sort of material from the subsurface to bubble up, to straw up, to bump up, some way, some mechanism to burst forward and make a dome and then spew, or just kind of what we would consider effusive, which means very viscous, sticky, just kind of all over the place. So nothing really spectacular, but hey, you know what? It can make for a really nice little dome there. And then sometimes these are all controlled by tectonic structures. So like I said, graben, or just very large fault systems, dike intrusions, which would mean some sort of material would just kind of crisscross its way into the subsurface and just kind of crack and brittle surface there. So here's our two domes. Now they're certainly not prevalent whatsoever, so they're much easier to see if you were to see them with a very powerful telescope for one, and a CCD camera. And you just need to angle it just right to get the shadow just right to get these two domes figured out. So again, this is where our domes are. So we have one really much in the Mare unit here, and then the one in the upper Mare unit. So slightly different in terms of potentially their mineralogy. Certainly their shapes are different as well. So the one that is not near our fabulous graben here, though, is quite skinny. It's quite tall, whereas the other one's very shallow and very mound-like. So between the two, though, so remember, dome one is the outsider, the one that's just kind of happy all by itself. There's no grubbing around to bother it or anything. Dome 2 is just like, there's a grubbin here. What's going on? Okay, so Dome 2, okay, has a larger volume. We've already seen that with just how mound-like it looks. So Dome 1 is more viscous. Whoa, goodness. I have no idea what just happened there. So Dome 2 has a much faster eruption magma rate going on there. And then Dome 1, because it's more viscous though, and it has a much slower eruption rate, it would honestly have a shorter emplacement time because it's so small and very tower-like in that regard. So steeper slopes, more viscous. It's a happy little dome. Dome 2, it took a while. It took a while to form. It has a much larger volume, even though it was faster eruption. It still needed a lot of volume to make that dome compared to the other one. Now another fun dome that I just recently got a paper about, which I was very happy about, is Fracastorius. So Fracastorius is a bit of a mouthful. It's really very fun to type up a paper over and over of that name. But this is what I mean by having some beautiful CCD imaging using a telescope here. So here's Fracastorius crater right at the limb of Mare Nectaris there, and here is our big beautiful dome right here. And you notice maybe that little hole right there, that's a vent. That's cool. Not all domes have a very evident vent right there, but yeah, there it is. It's a big pretty flat looking dome here though. All these little red markings here means that there would have been little itty bitty faults around the areas that may have helped push the material closer to this dome. Here's what the vent looks like using different kinds of imaging. We wanted to see what kind of boulders and shadows might be around the vent, how steep the slopes would have been in this particular area as well. Oh goodness. Okay. My computer. My goodness. All right. So switching out of domes for a hot second, and yeah, no pun intended here. Now we're gonna go into the very cold part of the moon that I work on. So this is the south pole of the moon. And notice now that we have not only just a plethora of very deep, dark looking craters here though, but just how dark a lot of this area is. And it really takes the phrase "where the sun don't shine" to a very literal sense. So this is just a snippet of a lot of the shadow work that we're dealing with. There are pieces of both the north and the south pole of the moon, but we're going to focus on the south pole tonight. But happy to answer questions about both poles. But the south pole of the moon here, we're really seeing that there's pieces of the moon that just never see any bits of sunlight here. And that is actually quite interesting because we get what is called permanently shadowed regions, or PSRs. So PSRs can vary in seasonal temperature. So you have the moon that is just slightly wobbling with its relationship with the Earth as well. And that little itty bitty wobble can give us different kinds of seasonal temperatures at those shadow regions. So permanently shadowed regions are not truly affected by the wobble. There are some regions that might just get just a little snippet of sunlight and it can throw off the whole thing. So PSRs are typically found at just below 110 Kelvin. So we're talking very cold here, and very much capable of cold trapping water over 1 million years worth. So to thousands to millions of years. So under 110 Kelvin though. So 110 Kelvin, we're talking 300 some negative 300 degrees some Fahrenheit. Now it can get colder. So the fun part about these is that it can get just as cold as Pluto, winter on Pluto, on the moon. That is very fascinating to think about, though, because the moon is not just trapping water ice at the poles here, though. We're also trying to figure out what else could be frozen at these craters as well, but also a number of questions as well. So how are they formed? What type of ice are we dealing with? Because there might be different kinds of ices, which I will say, yes, there is, and I'll show you guys examples here in a bit. But because there's different kinds of ices, do they all freeze and sublimate differently? Do you find one versus the other in different spots around the poles of the moon? How would they have accreted there in the first place? So I can answer that question, at least right off the bat, is that it maybe they all came from different sources. So a lot of the hydrogen and oxygen on the moon would have been from cometary material. You have comets flying by or crashing into the moon, and then we get all of this reservoir of material from a comet. But there's times when we can also have material from asteroids as well. We can have material from volcanic activity on the moon, and it would have released some sort of gas, vapors and whatnot. And then all that gas and vapor, they want to immediately find a safe place. They want to go run and hide. Any kind of vapors just kind of bouncing around the moon there. And sometimes you could get solar wind. So you have just happy little molecules just minding their own business. You get the solar wind just blasting the surface of the moon. Again, those molecules are like, I want to run, I want to hide. So all of those poor molecules will start skipping to the poles and just immediately hide into a deep, dark place, literally, and then freeze there, and make their own little frozen communities in there. So all of these different kinds of volatiles, though, so we can have sulfur and carbon dioxide and possibly methanol and ammonia and everything. So I'll show you guys again examples here in a bit, but it's all about location, location, location. Where are your dark areas? And then make sure that they are dark for a very, very long time and deep. That would help too. So there's all these different kinds of craters, and notice though that a lot of them are off to the side of their host craters as well. That not all craters is just fully filled up with these kinds of ices. So I'm on the Diviner science team. So Diviner is our radiometer on the Lunar Reconnaissance Orbiter. So radiometer just means just big fancy thermometer, and give us very pretty, very rainbow-like images of the moon. Now we get this all across the moon. We have global maps of temperatures across the moon, though, but getting polar data, both north and south pole of the moon from Diviner, has been quite the challenge, to be sure, for the LRO, Lunar Reconnaissance Orbiter, but we do have plenty of maps. So while we totally wish that the moon was this beautiful colors and everything, though, but what we're seeing are temperatures here. So temperature in units of Kelvin here. So we're looking at blues and purples here. So all of this blue and purple stuff is very much under 100 Kelvin. It's very, very cold stuff going on. Whereas the rest, the average bits of the moon here are in the lovely like 200 Kelvin there. So nice and warm. But again, we're not just dealing with water ice. Different kinds of chemicals can freeze and do a bunch of other really cool stuff at different temperatures. So water sits very prettily around 120 Kelvin. So once it hits 120 Kelvin, it's pretty much frozen in different aspects. Sodium and sulfur volatiles can freeze at higher temperatures. That's or at least exist at higher temperatures, and they can freeze way below their that temperature of 200 for sodium and 250 for sulfur. But you get into much, much colder areas, which we do have at a lot of these craters, and we get methanol and ammonia and hydrogen sulfide and sulfur dioxide. Okay, that's going to pose an interesting challenge for our eventual astronauts, to be sure. Carbon dioxide, yeah, that's fine. Methanol, really, really tiny, probably nothing to worry about. Ammonia, okay, we're getting into some like corrosive territory here. Then you get hydrogen sulfide and sulfur dioxide, two very, very tricky and very challenging volatiles to deal with, mainly because they're extremely hazardous to not only poke and prod and dig up, but also they can be very finicky, that as soon as they start to warm up, they can just release. And that's not going to be good. So a lot of these different kinds of ices are certainly going to be an interesting challenge for not just our astronauts, but certainly for future landers and rovers. So a really pretty rover that I'm super excited about is the Viper rover. So Viper is, I believe, the volatile interaction. Oh, goodness. There's so many acronyms to keep track of at NASA. And yep, something with volatile interactions and exploration rover. So Viper is going to have all sorts of different kinds of instruments, though. But one instrument that's going to be really exciting to have is it's going to have a drill called Trident. So the drill is going to just a little itty bitty drill, just kind of drill into the surface, take up a little bit of the sample. We're going to shine a little flashlight into it. There's going to be little spectrometers that are going to look into the hole and go like, oh, cool, there's water ice, great. There might be some carbon dioxide, great. Maybe some ammonia, okay. Maybe hydrogen sulfide, okay, moving on, and let's make another hole. So this little Viper is underway. I believe it's scheduled for late next year, I believe it got pushed. Another fun orbiter to look forward to later this year is Lunar Trailblazer. I love their logo here. And if you get a moment to really hone in on their logo, there's all sorts of really pretty clues as to what their mission is about with their logo. So props and congratulations to whoever made this logo, because it is absolutely beautiful. So NASA Simplex just means that it's what type of mission it is. So Simplex means that it's a very small CubeSat-like orbiter that's going to go around the poles of the moon, and very much a low budget, which is fantastic. But notice all these little bits of dots here and there. These are water molecules. So that's one fun little Easter egg here. Another Easter egg, it's a little bit hard to see here though, but you got a red beam and a blue beam. That's because it's going to do two different wavelengths of channels to find the water ice. So that's another Easter egg there. There's the South Pole of the moon. So there's our next Easter egg. And then you might notice like, oh, well, this looks really pretty though, with all the, it's very rainbowy and, but why is it dipping like this? Is because that's what water ice looks like in the infrared. It's just a nice big low dip that we are specifically wanting to look for with Trailblazer in that regard. So just a fun Easter eggs all around with this logo. So I absolutely love it. And then, like I said, with Artemis coming up, so Artemis 1 was a success. We're gonna, we're quickly getting ready for Artemis 2, which is another dress rehearsal for us. Artemis 3 is where the real action is going to begin, where we're gonna finally have boots on the ground, and we're rapidly gaining momentum to finally narrow down the landing site for Artemis 3, which is really, really exciting. But oh boy, that's a lot of work. So one of many meetings is actually going to be coming up in about 2 months, and I'll be attending that as well. But Artemis, what kind of instruments, where are we even landing them? The main priority with the Artemis 3 folks, at least, is that we want to know more about the ice. But we need other smaller, cheaper missions ahead of time to kind of scout it out for us. So hence why we have Viper, why we have Trailblazer going ahead of time. There's a couple other smaller missions to come up as well called CLIPS missions, but those are scattered about. Not all of them are going to the South Pole. So for Artemis, we're focusing on the South Pole, but it's still a matter of what are we going to do? It's how do you safely capture the ice without obviously melting the poor ice, and without also damaging your instruments as well, if you're dealing with something that's very corrosive or something potentially hazardous and dangerous to the astronauts as well. So designing all these instruments, how are they going to study it? What exactly are they going to study it? Where are they going to study it? All of this is still being encompassed. We at least know the why, and all that's been wonderfully documented already. And feel free to Google the Artemis 3 science report, and it's a beautiful PDF page as to like what are the priorities of Artemis 3, what is the priorities of future Artemis missions as well. And so all of these different kinds of questions regarding the ice at the moon, what kind of ice are we dealing with, how did it get there, how deep does it go as well, could versus like the just surface level of what we're seeing here. Could there just be very large reservoirs of ice? Could there just big, beautiful ice chambers underneath all these craters? We don't know. That'd be cool. And then in that case, what about classifying these different kinds of cold spots as well? So once we get through Trailblazer and Viper and Artemis and so on and so forth, could we essentially make a better map system of all of these different kinds of ices? And I don't just mean like, okay, this is a good spot to dig, don't go over here because there's way too much hydrogen sulfide. That place is a no-no. Not necessarily, although that will help as far as safety and hazards go, but that could also tell us a lot about, okay, why would that spot over there have hydrogen sulfide and not over here? What does that really mean as far as like the chemistry and the physics involved with the accumulation of the different kinds of ices? So that's something else to look forward to, is maybe a map of these particular icy spots though. So there's so much to go on as far as the hot stuff on the moon with the volcanic systems, and we're going to have at least one lander and or rover toward at least the Gruithuisen volcanic domes, maybe a few, but there's domes all over the place. And then a lot of exploration in the deep, dark, cold regions on the moon as well. So there's a lot to do with the moon. Whether it's still geologically active is still up for debate as well. We had seismometers from the Apollo missions. We know that there are moonquakes. We're going to be sending another seismometer on the far side of the moon coming up. That's called the Far Side Seismic Suite. That's a mouthful, but that's going to be exciting because that's going to give us a way more updated, more high-tech seismometer, built by and managed by the same folks that did the InSight seismometer on Mars. It's pretty much nearly the same team. They're just wanting to do the same thing on the moon, which is exciting. So now we're going to find out more about quake activity on the moon, hopefully more instances on volcanic activity. Now, are we going to land near a volcano and it's going to start exploding all over the place? Probably not. But it's still a matter of how did it get there? Why are there different domes here and there? Why are Gruithuisen domes so special versus, everywhere else? Like Fracastorius. It's a very large pancake-like with a vent in the middle. Why? Whereas some domes, you don't even see a vent. Why? So all of these different kinds of questions are very exciting with the hot versus the cold bits of the moon. And with that, I'm happy to answer any questions anybody may have. So thank you so much again for having me this evening.
Okay, yeah, that's fabulous. So everybody's welcome to unmute themselves and give Caitlin the business.
I got two quick questions, Caitlin. Are there any lava tubes on the moon?
There are lava tubes on the moon, so that there could be some interesting things going on with lava tubes, though. It's something that needs to be done is where would be the safest lava tubes, not only for hopefully eventual exploration via astronauts, but could we send like a little itty bitty scout rover to one of the lava tubes? And so there's two things going on right now, is looking at where the lava tubes are and are any of them collapsed? Because if you have a halfway collapsed lava tube, that may not be wise to go sneak in there. The other part of this is that we have teams out of Goddard and a few other folks at other NASA centers that are going to other lava tubes around the world, mostly in Hawaii, and a little bit in Canada too, but mostly in Hawaii, that are testing instruments to make it easier and potentially portable for astronauts to go explore lava tubes. So that's also exciting too, is that we're already thinking about what kind of technology we can have for astronauts to go explore those lava tubes.
Do they have any particular more likely places to find helium-3 than others?
Very good question. So the thing about helium-3 is that we need to have better detections of it. So we do know it's there. We absolutely know it's there. The issue is that the technology we had at the time, I love LRO. It's fantastic. We need more instruments to get a better sense as to where it is. Our resolution isn't terribly great for that. So we need more data.
I really find it interesting what you're doing, because back in 1963, I won second place in the Queens, New York Science Fair for making a Moon Explorer robot that I could demonstrate to move around, and had a light and a magnet and treads, and I could demonstrate it. And out of all the kids that entered the Queens, New York Science Fair, second place is a pretty good spot for a ninth grader.
That's fantastic.
Yeah,
I love it.
So you're doing what I kind of did 50 years ago. Oh my God, I'm old.
Don't dwell on
Thanks.
it. Don't dwell on it. You're welcome, but don't dwell on it.
All right, Paul, you have a question.
Yeah, just a question would be, do you ever want to go to the moon?
No. You probably didn't expect that answer. Nope. So my whole deal is that I could happily train them. I could tell them what rocks for them to bring back for me. I'll happily train them. I could tell them where all the pretty rocks are. I could tell them where not to dig. Or don't lick the rock. Don't lick that rock. Don't do that. But I'll happily tell them that, and they can bring the rocks back to me. I'll be fine right here.
When do you think the moon, there'll be enough population on the moon to do real science up there? What year? 2050?
No. If
Much
I'm
earlier.
early estimates, it's gonna take a while for sure to at least have any sort of population. We're gonna end up going back and forth just a few more times. Now, building moon bases that are temporary housing, I think that's going to be an interesting first step, but not permanent housing, not for many decades still, because we're still learning about the material science and the engineering of how to even build a dome on the moon. The really interesting technology that's coming about is not only 3D printing, because now you can 3D print whole houses nowadays, which is fantastic, but it's not like you're going to rocket up a cement truck to the moon or anything. So what's being done right now is, can we make our own cement with lunar soil? So University of Central Florida and Kennedy are teaming up and actually having simulated lunar soil. So simulated meaning that they took the same bits from the Apollo samples and really looked at, okay, what percentage of iron, what percentage of manganese, what percentage of nickel, aluminum, and so on and so forth. What percentage of all these different kinds of minerals? We're going to make our own dirt based on that. And then we're just going to play with it and see if we can make our own cement and then try to figure out how to 3D print it. And guess what? It's starting to work and it looks really cool. So so some exciting stuff coming up with that on, it's fascinating to see how much 3D printing has come about. 3D printing was hardly around when I was an undergrad. So it's like, oh, this is a technology now. Okay, what do we have to learn with this? And but if we could do this very cheap and on the go and use the materials already there on the moon, fantastic. One less cement trunk that we have to rocket to the moon.
Mario,
always thought-
you have a question.
Hmm?
Mario has a question. Unmute.
Nope,
still
still can't hear you.
Raise it up.
There we go.
Oh, there you are. Hi.
All right, good. Sorry, but I had earplugs in. So my question is, you showed that there's evidence of water, and we know that it's in the poles. What's the best estimate of how much water there is? Is it sustainable for a community in any one location, or is it so scattered that it'll be very difficult to mine?
So surface level, it's very scattered. So this is why we want to figure out if there's any depth to a lot of this ice. We're thinking probably, but how pure it is depth-wise, probably not, is my guess, but who knows? We obviously need to dig and make core samples of those ices. So that's definitely going to be something that Artemis 3 or 4 are going to have to figure out how to do that carefully, because coring ice is very difficult and very finicky as well. And we've done it all the time with like the Arctic and the Antarctic, sure, but we're dealing with -400 some degrees Fahrenheit. Yeah, that's going to be a bit tricky to keep any of that ice from melting and sublimating away with a drill. So depth is going to be our best guess for using it as a resource. But if we were just doing complete surface level, it's very scattered.
Tony, you had a question.
Yeah, so hey, Caitlin, thank you for the great talk. And related question, do you have any dates on the orogeny of your domes 1 and 2? And if so, how do you know that?
So date wise, we probably have an estimate as to how old they are. But
And
that
what
is
would
still we're correct. So probably however old an Imbrium unit is. I'm thinking of geologic units on the moon though, but how old is Imbrium? Oh goodness, I would have to look at
Are we talking like
at a
3.5
better
billion
map.
or so, or when was last date of the lava flows in those regions? Then do we know that?
Correct. Yeah. So the Imbrium impact may have reawakened some of that material and just kind of may have shifted some of that material and just kind of went, boop, there's a dome.
Sure. It's a cool question though.
Oh, for sure, for sure. So we're still very much writing up the paper too, though.
Cool. Thank you.
Mm-hmm.
Bill Wall, you have a question? Unmute.
Yeah,
There you go.
unfortunately, I missed the first part of your talk, and maybe you've answered this question in one way or another. It sounds like you might have. But the specific missions that you mentioned, how do they set the stage for long-term colonization?
Very good question. So setting the stage for that is we need to be better. We're having a uptick in scouting ahead of time. That's our major big thing right now is before we even set foot on the moon, before we go like, oh, we want to build a dome there, send a scout. And by scouting, I mean CubeSat orbiters that can be done very, very cheap and on the go, landers, rovers. So sending all this robotic scouts out first. So that way, not only we can see what the landing site is like, and is it really worth it, but also we still don't understand the lunar environment as a whole either. If we land somewhere and we're like, oh, there's maybe a lot more iron in this particular area than we thought. Or oh, you know what, maybe we don't get as much Earth to moon communications in this particular spot as much as we thought either. So having scouting parties essentially is that step first to eventually get into civilization. So again, it's all about learning the environment, especially if we're wanting to send boots on the ground astronauts to the South Pole of the moon. Not only is it cold, which is a whole, it's a whole issue all in itself. But again, remember that the images here of just how dark a lot of these places were. That darkness also affects your communications as well. If it's dark, you're not going to see Earth. You're not going to be able to communicate with Earth whatsoever. So you have to find pockets of your timing too, and make sure that you're just on the right spot on the rim of a crater and go, hey, Earth, we're still alive. Okay, and now back down into the crater and do some more digging.
Yeah, I don't think darkness is the problem, because if there's always one side of the moon. If you're on the side of the moon that's facing the Earth, you can still be dark and be facing the Earth. So
not necessarily on the
no,
south
not
pole
necessarily,
of the
but
moon.
over like half the moon's surface. If you're like at new moon, the whole side of the moon is facing towards you and it's dark.
Not the south pole of the moon. So not
Well,
necessarily.
there are certain places, yeah, true, but most of it, yeah, I see what you're saying. Okay.
Yeah. So if we're doing boots on the ground at the South Pole of the moon, it ain't gonna matter what phase we're in. But again, it's still finding those pockets of time.
Sure.
And go, okay, we're only having astronauts be there for 6 days. How much of those can we find 6 days, or even just squeeze it to 5 days? Because again, also a lot of our technology is still solar powered as well. That's going to be an issue with batteries. Now, some rovers are half and half with nuclear batteries versus solar power batteries. So Viper is a good example on this one. So Viper does have a little bit of solar panel energy going on, but it does have some batteries for some of its instruments to at least keep warm, because it's going to be in a very, very cold place. But all of the, so again, also technology, having landers and rovers ahead of time can help us test these technologies ahead of time too. So battery technology is very much becoming a really fascinating branch in NASA and even private space companies as well, because also we want to explore the outer solar system better as well too. Our battery systems were pretty much tested successfully with the New Horizons mission out to Pluto. It got to Pluto in 9.5 years. Most of its instruments are still going strong, and it's running on plutonium. It's going great. But can we make the batteries different in some way using different materials? Can we make them smaller? Can we make them last longer to get to Jupiter and Saturn and hopefully eventually Uranus and Neptune and so on? But at least with the moon, we can test all of these technologies with robots, and hooray, more technology development.
To solve the communication problem from inside the craters and stuff, I think we should engage Elon Musk to set up like a Starlink I mean, if you think of it, if the orbit, he would be, if you're inside the crater, okay? If you had orbiting satellites like you did, communications, you could talk to the satellite over you, which could relay it to back to Earth probably. I don't think that would be as big a problem as it sounds. You're talking about CubeSat satellite.
Correct.
I agree, yeah.
It's only, what, 6 inches by 6 inches, you know?
Correct. Yes. So yes, absolutely. So having some sort of CubeSat or Starlink relay, absolutely. So those are very much under discussion as well. Another issue that we're running into though is not just communications from the moon. How do we receive communications from Earth as well? So Earth really heavily relies on the DSN, the Deep Space Network. The issue with all this now with Deep Space Network is that everybody uses it. All missions in space use the DSN. So there's only so much bandwidth that we can do in such a short amount of time with certain missions. So like New Horizons is in hibernation mode until mid-March. So right now, New Horizons, it's still pinging, going like, I'm still flying, I'm still alive. So thankfully not as much power as say the Mars Reconnaissance Orbiter, or the Lunar Reconnaissance Orbiter, and then most of our Earth satellite relays as well. So getting the timing right as well for uplinking and downlinking all the data, all the signals, all the communications. All of that is being planned right now, and it has been for some time. We're getting ready to have all of this Artemis activity going on. So by all means, communications are underway, not my area of expertise, but I can guarantee to you that everybody is running around right now just going like, oh, have we thought about this yet? All the contingency plans.
So I have a quick question that'll get you a little bit back to the science. And it has to do with the hot spots and the existence or prior existence of what a type of volcanism that was called fire fountains. Have you ever heard that phrase before? And
Yeah.
that's the cause of the tiny spherules, the glass spherules that were collected by the astronauts, and which people at schools can see because there's these lucite blocks which have these spherules, the regolith embedded in them, and you can study them under a microscope, which I was able to do at my school with some kids and other teachers. And there they are, the glass spherules, something which is totally unique to the moon compared to here. And they say that these glassy spherules, which are green and contain water with the same isotope as our water, was created in a process called fire fountaining. So I'm asking you, what is fire fountain?
So fire fountains are an interesting type of volcanism because they don't necessarily come from a dome. So think of it as just a very dusty geyser. Then you have some sort of vent going on, but no dome, no sticky material that is just like accumulating, makes a dome and then blah, 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 of material and whatnot. But more of a very rapid burst of pressure, of overpressure, if you will, then of material, of glassy material that would have just kept building up and then very much geyser-like. So ring, very fire rings here is that it would just immediately land in like a halo. Now there's a really pretty halo that I could probably do a really quick Google search for and share it with you. It's around Oriental. It's called the Dark Halo, which it sounds very ominous, but it's actually really quite pretty. Let's see. So let's see if I can actually share that. So this is near Oriental Basin, and so all of this is dark glassy material that would have spewed probably around there's some holes here, craters and holes and whatnot. So somewhere in here, and then it would have spewed up and then formed this dark halo of material here.
And when
So
was this epic?
that's a good
Early in the history of the moon?
good question.
First billion years or so?
Yeah, probably. I know someone, yeah, James Head out of Brown University wrote a beautiful paper, this one in 2002, that goes through how big it is, how wide it would have been, when would it have formed. So it would have lasted only 1 to 2 weeks. So very, very quick. Very, very quick material, because most of domes take a minimum of 1 year to even form. So it just in a matter of weeks to do this though. But this paper is freely available for anybody who wants to check it out. I'll go ahead and just paste it into the chat here as well. Everybody can read about the mysterious dark halo of Oriental.
Thank you.
Mhm.
Any other questions?
I got a million of them, but I don't think you can answer them all.
Only so many hours in a day, right?
Yeah, for sure. I was, the moon is kind of a byproduct of a collision between something and the Earth, as, okay, it got ejected. So almost everything that's down here should be up there, minus the volatiles and the fact that, okay, now you're in vacuum and things are spewing away. But under the crust, it's got to have 80%, 85% of what we got down here that didn't boil off. So it's a depth issue, and when you're talking about making cement, I thought they already had powdery, stuff, crustal material that was all over everything on the astronauts. And all you need to do is take the water and this dust and a couple of rocks and you got concrete or something close. So, you don't have to bring coals to Newcastle. It sounds like everything is right there. You just got to get at it.
Yeah, exactly. And that's the beauty part too, is we're still learning about all the kind of materials are at the moon, because it's not uniform all over the place. So where would be the best spots to get your best cement?
Sure. Great lecture. I mean, a great informative presentation, and I certainly appreciate it. I'm sure everyone else does.
Thank you.
Caitlin, great talk. I work with Jim Head mainly on the Mars,
Oh, hi.
but he tasked me a few years ago to do models of the glaciers on Mercury in the permanently shadowed regions on Mercury.
Mhm.
And bizarrely, it's the only paper I've ever gotten that the press picked up. Glaciers on Mercury. So
That sounds beautiful. Could you please send me that paper? I'd love to read it.
okay, yeah, sure. I think it's Icarus, but something like that. But what I got from your talk that I had never thought of was the other volatiles. I was only working with water. How's the water going to behave in these permanently shadowed regions? But what you bring to this is all these other things that are going to screw everything up, including the mechanical properties of the water if it's there. So thank you very much for that. I appreciate it.
Exactly. Well, and that's most of my job at Goddard is going like, ooh, what kinds of other ices are coming about? But you're right. I mean, another thing to look at this too is then we need more experimental data too. All of these different kinds of volatiles existing under -300 some Fahrenheit. We don't understand the mechanical thermophysical properties of those kinds of chemistries, compounds, ices, mixtures, anything. Very, very little. Water ice, yeah, we've known what water ice does for decades now, but I want to know what hydrogen sulfide does at 10K temperatures. That would be cool. I have no idea what it does.
And
You know
that
anything
no
about
pressure.
amorphous ice, amorphous water ice, the kind of ice that forms when H2O sputters onto a surface at 100 Kelvin, and it makes this stuff called amorphous ice that supposedly is mechanically very soft. And you know anything about it?
I do. And just to make matters complicated, there are two different kinds of amorphous water ice that can be high density and low density. So let's just complicate everything here.
It's soft. At 100 Kelvin, it could potentially flow, is what interested me.
Potentially. Again, we just need more experimental data because we're also on the assumption in that regard that it's pure and it's not. So what happens if you add methane or carbon dioxide into the mix? How does that change up your mechanical behavior of your water ice now?
I love Pluto too, and all the glaciers on Pluto.
Oh, you and I need to chat glaciers on Pluto because that's what part of my PhD was about.
Okay, I'll email you.
Thank you.
That's great. We got a little linkage going. Well, I think the time is up unless we have any last questions. If not, I will close this out with by thanking Caitlin. You guys, you did so great that we're going to let you stay on Earth.
Much
Thank you, Caitlin.
appreciated. Woo.
Great job.
Yeah, thank you very much. I hope to hear a lot more from you as time goes on.
And
Thank you.
thanks, Bill, for bringing it to us.
Yeah.
Great enthusiasm. Love it.
Super
Thank
duper.
you.
Thank you, guys.
Have a
Yeah.
great night. Have a great weekend.
Okay, great. Thank you. Bye.
Bye-bye.